Today's lesson focuses on the VSEPR theory. This is a theory created by Ronald Gillespie, who is pictured here, and is credited with working at McMaster University. So there's a bit of a Canadian connection. And the VSEPR theory is used to predict the shapes, the three-dimensional shapes of more complex molecular structures. So although it's pronounced VSEPR, it's not really written like that, and it's an acronym that stands for Valence, Shell, Electron, Pair, Repulsion Theory. And so what we're thinking about now is as we transition from Lewis structures, which are a two-dimensional representation of bonding, we're now going to be looking at three-dimensional structures as they naturally exist. And what is the implication of the electron pairs, as we know that they do repel, and what does that do to the structure of the molecule and how does it change it? So we know that these electrons want to stay as far apart as possible to minimize repulsion. So they're all negatively charged and they are repelling and trying to get away from each other. This VSEPR theory is going to help us predict the geometry of the molecule. There are 5 main shapes that these structures take on. And what we have to do is look at the central atom of our molecule. And this central atom will determine which of the 5 shapes the structure will take on. There are some very simple rules of the VSEPR theory. And the first thing that we want to be aware of is that we really only care about the central atom and the valence electrons that surround that central atom. They are important because they are going to determine what kind of molecular shape our molecule will take on. We also already know that electron pairs repel each other. And this is true whether those electrons are bonded to two different atoms, or whether they're only bonded on one side, or sitting on one side of an atom and they're actually not bonded, or they are lone pairs. We know also that the electrons are going to assume orientations in order to minimize repulsion. So they're trying to get as far away from each other around the central atom. The closer two groups of electrons are forced, then there's going to be more repulsion between them. And one thing that we need to be aware of is that the lone electron pairs actually have more repulsion or more negativity than the bonded electron pairs do. And this is just because they don't have attraction for the nuclei of an atom on the other side of them. We're going to talk about that a little bit more in a future slide. So now as we transition from Lewis structures to a three-dimensional structure using VSEPR theory, we have to follow just a few simple rules. So we first draw the Lewis structure of your molecule. We've gone over that in a lesson. Again, it could be a simple molecule. It could be one that expands its octet. It could be a polyatomic ion. And then what we do is around the central atom, we count the total number of bonding pairs and lone pairs of electrons. So you count them up. And then depending on how many electron pairs are around that central atom, you are going to fall into one of these 5 shapes. So linear, trigonal planar, tetrahedral, trigonal bipyramidal, or octahedral. And based on these shapes, there's going to be very specific bond angles that your bonded atoms and your lone pairs are going to assume around the central atom. So here are the 5 shapes that can exist with VSEPR theory. And so if you have a central atom, so the central atom here is represented by A, and then if it's bonded to 2 other elements like this, so here's carbon dioxide right here, in order to maximize or minimize repulsion, these electron pairs right here are going to get as far away from each other as possible. And when there's only 2 bonded atoms, they take on this 180 bond angle to get as far apart as possible. Once we start to go up to 3 bonded atoms, we take on a shape called trigonal planar. Oh, sorry, the first one's called linear, if I didn't say that. Trigonal planar has 3 bonded atoms, as you see here. And in order for those electron pairs to get as far away from each other, they take on a 120-degree angle. When we have 4 bonded atoms, as we see right here, the shape is called tetrahedral. And in a 3-dimensional structure, the bond angles are actually 109.5. Very frequently, we draw tetrahedral shapes with 90-degree angles, something like this. If we were thinking of like methane, right, in organic chemistry, that's 90-degree angles, but that's not correct. We don't account for the 3-dimensional structure. So it actually looks like this, and the bond angles are all 109.5 to get those bonded atoms as far away from each other. If you have 5 atoms that are bonded into the central atom, we call the shape trigonal bipyramidal, and it's a combination of some 90-degree angles. Okay, so there'd be 90 there. We can see there's a 90-degree angle there. And then around the middle here, that's actually a trigonal planar kind of shape right here, and they take on 120-degree angles. And then lastly, and these 2, by the way, at the end here, these are central atoms that expand their octet. So if we had a central atom that had 6 bonding sites, we call this octahedral, and all of the atoms, all of them, have a 90-degree angle. Let's take a look at what happens when we have some lone pairs. So let's pretend that we have a tetrahedral shape here. And in the first one right here, all of our bonding sites have atoms. So notice how elongated the electron cloud is, because again, you've got a positive nucleus in the carbon and you've got a positive nucleus in the hydrogen that's attracting these electrons on either side, and it pulls the negativity, across the bond, and it elongates it. Everything here has bond angles of 109.5 because all of our bonding sites are taken up. As soon as I have a lone pair that I see right here, so here's the ammonia molecule. Notice now how the negativity around the lone pair is bigger. And again, it's because it doesn't have anything on the end here to attract those electrons and elongate the electron cloud. This area of negativity pushes down on your bonded atoms, and it causes the bond angle in between to tighten up a little bit and decrease to 107.3. Here in water, where you have 2 regions of negativity that are not bonded, notice how much bigger that repulsive area is. And again, it pushes down on your bonded oxygen-hydrogen bonds, and it tightens up the bond angle to 104.5. These are things you have to be aware of as we go through and we draw structures now. You need to show that the bond angles change, that they either become greater than or less than the standard bond angle. So I'm going to do 2 examples with you. I'll leave the other 2 examples that are there for you to try. And we're going to go through and go through all the steps that are required with VSEPR theory. So we're going to show the bonding for boron trihydride. The first thing that you do is you draw your Lewis structure. Lewis structure is rough work. Okay, so for boron, boron has 3 valence electrons, and we're trying to bond in a hydrogen. A hydrogen has 1 valence electron, so we'll make a bond angle or a bond there, a bond here, and another bond right here. And remember, we now are most worried about the central atom, and we count up the regions of electrons. So I have a region of electron here, here, and here. So I have 3 regions of electrons. When I have 3 regions of electrons, those electrons are going to try to spread themselves out as far as possible, and they're going to set themselves up like this. These are 120-degree bond angles, and the name of this shape, so the VSEPR name, is called trigonal planar. The VSEPR notation is that I have a central atom, which is A, and 3 bonded atoms, so I write AX3. I have my VSEPR diagram, it looks like that. I have my bond angles, and then I have to talk about polarity. Well, this is a symmetrical molecule, so you can figure out the difference in electronegativity between boron and hydrogen. I'm not even going to bother because I can tell that even if those were polar bonds, this is equally distributed across. And so this becomes a non-polar molecule. Let's do the next one. So with water, we draw the Lewis structure. So water, the oxygen has 6 valence electrons. We bring a hydrogen in and we bond it to those single pairs. So I have a bonded pair of electrons right here, a second pair, and then I have a pair of electrons that are not bonded and a fourth pair. So I have 4 regions of electrons around the central atom. And so I'm going to now call it by its VSEPR shape. So the order doesn't matter with which you write down all this information, but this is a tetrahedral shape because I have 4 regions of electrons around this central atom. I'm going to draw the molecule over here to the side. So what we have is we have a pair of electrons, and this is how we represent them with a line, like a bonded line, but the electrons are at the top of that. And remember, tetrahedral we often show with 90-degree angles. Don't do that now. So you'd have another pair coming sort of downwards. You have a pair of electrons bonded to hydrogen that are kind of coming out at you. So this is like a bit of a triangle, a shaded in triangle. And then you would have a pair of electrons extending back behind the plane of the screen, for example. Okay, so this is the structure of water. And then we talk also about VSEPR notation. So let's get the VSEPR notation. We have a central atom. We have 2 bonded atoms. And then we have 2 lone pairs of electrons. So that is denoted by the letter E, and that would be my VSEPR notation. We've done the VSEPR name. I have the VSEPR diagram. Bond angles. Okay, so we know that in a tetrahedral that all the bond angles are 109.5, but that's true if everybody's bonded. They're not all bonded. These electrons are going to cause more repulsion. And so what we want to do is we want to indicate that right here, my bond angles are less than 109.5, okay, because of repulsion. And then right here, my bond angles are actually greater than 109.5 because I have repulsion and those electron pairs are pushing themselves away further. The bond angles actually get bigger. And then polarity. Okay, so polarity is not new. We've done it a bunch of times. We should know with the water molecules that the difference in En is 1.24. Between oxygen and hydrogen. This becomes a polar bond. And we know we get bond dipoles running this way, and we have an overall dipole running through the molecule like that. So we write in polar shape or molecule, whatever you'd like. Now, give these ones a try. So we have carbon tetrachloride and we have sulfur tetrafluoride. Show the Lewis structure, count up the regions of electrons. The biggest challenge for you will be drawing the 3D structure, although these are things we're going to practice in class. And we're going to actually get out molecular models so that you can see them visually and have a 3D representation right in front of you. But try your best to do these 2, and then we'll check your answers in class.